Welcome back to the deep dive, everyone. This is where we, try to cut through the noise and get to the heart of what's happening in AI.
Glad to be here.
Today, we're taking a really fascinating plunge into something absolutely fundamental, but maybe not always talked about: activation functions in neural networks.
Oh yeah, critical stuff.
If you're a tech enthusiast, maybe a developer, or honestly just curious about what makes AI like ChatGPT or those amazing image generators actually work, well, this is for you. It's kind of a shortcut to understanding the engine room.
It really is.
Yeah.
Because at its core, an activation function, its job is to introduce non-linearity.
Non-linearity. Okay.
Yeah. Think about it like building something complex, but all your parts are just straight lines.
Yeah.
You can't build anything interesting.
Right.
You need curves, angles.
Right.
That's what activation functions do for a neural network. Without them, it's basically a fancy linear model. It couldn't learn complex patterns, like understanding language or seeing a cat in a photo.
So they're the things that let it handle the messy, non-linear real world.
Exactly. They're the secret sauce. It's why even relatively simple networks can, in theory, approximate almost any continuous function. That's the universal approximation theorem, basically. Huge power.
Okay, let's unpack this then. Our mission today is to explore how these functions went from, well, simple ideas to tackling some really tough AI challenges. Things like the dying neuron problem.
Yep, that's a big one.
And how they paved the way for the performance we see in today's giant models.
It's a cool story of evolution, driven by problems.
So to really get why the new ones are so important, we probably need to look back first, right? Understand the issues with the older ones.
Definitely. The early functions, they were foundational, but yeah, they hit some walls pretty quickly, especially as networks got deeper.
Like Sigmoid and Tanh. I remember those from early courses.
Exactly those. They were super important initially, but they had this major flaw, the vanishing gradient problem.
Ah, okay. Explain that a bit more.
So imagine the network learning. It figures out its mistakes and sends a signal backwards saying, okay, you need to adjust this much. That signal is the gradient.
Right.
With Sigmoid and Tanh, if the input was really large or really small, the function flattens out, right? And the gradient there becomes tiny, almost zero.
Okay.
So as you pass this tiny signal back through many, many layers, multiplying it each time, poof, it vanishes.
Like a whisper down a long line.
Exactly like that. The layers, way back at the start, they get no signal. They just stop learning.
Wow, okay. That cripples deep learning.
Totally. Tanh was a little better than Sigmoid because its output was zero-centered, which helps training a bit, but it's still flattened out and had the vanishing gradient issue.
So if the signals were just disappearing, what was the next big idea? How did they try to fix that?
Well, that leads us to ReLU.
Yeah.
Rectified Linear Unit. That was a game changer.
How so?
It's super simple. If the input is positive, it just passes it through. If it's negative, it outputs zero. So for positive inputs, the gradient is constant. It's just one, no vanishing. And it was computationally really cheap. Networks started training much, much faster.
Sounds perfect. Problem solved.
Not quite. ReLU brought its own baggage. The biggest headache, the dying ReLU problem.
Dying ReLU. Okay, what's that?
Remember, it outputs zero for any negative input.
Yeah.
Well, the gradient for negative inputs is also zero. So if a neuron happens to get stuck always receiving negative input, its output is always zero. Its gradient is always zero.
It just stops learning permanently.
Pretty much. It becomes a dead neuron. Right. Doesn't contribute anything. And if too many neurons die, your network's capacity just tanks.
Yikes. Okay, so that's a major drawback. Any other issues with ReLU?
Yeah, a couple. Its output isn't zero-centered. All the outputs are zero or positive.
And why is zero-centered better again?
It helps the optimization process. Think of it like trying to balance something. If the signals are always pushing in one direction, positive, it can make the learning path kind of zigzag inefficiently towards the best solution. Zero-centered outputs help keep things balanced.
Okay. So less efficient learning.
Can be, yeah. Plus, there's that sharp corner at zero where it's technically not differentiable, which can be a minor annoyance for optimization. And since the positive output isn't bounded, there's a small risk of exploding gradients in some situations, though less common than vanishing ones.
Okay, so ReLU was a big step, but definitely not the final answer. This is where it gets really interesting, right? Researchers had to get more creative.
Exactly. They realized they needed something more nuanced than just on or off. Okay. This led to ideas like non-monotonicity.
Non-monotonicity. What does that mean?
Most older functions were monotonic. As input goes up, output either always goes up or always goes down. Simple.
Right.
Non-monotonic means the output can actually dip back down even if the input keeps increasing. It adds these little bumps or wiggles.
And why is that useful?
It gives the network more flexibility, allows it to learn much more complex, intricate patterns in the data. It's not just drawing straight lines or simple curves anymore.
Okay, so that brings us to the newer wave. Functions like Swish, Mish, and GELU. Let's start with Swish, or SiLU, right?
Yep, Swish or SiLU, Sigmoid Linear Unit. Google developed this one. It's defined as x times the sigmoid of x.
How does that help with the dying ReLU problem?
Well, it's smooth, no sharp corners like ReLU, and crucially, it has this property called self-gating.
Yeah, self-gating.
Yeah, the input value x actually helps control how much of the signal gets through via that sigmoid multiplication. And importantly, for negative inputs, it doesn't just output 0. It outputs a small negative value.
Ah, so the gradient isn't 0.
Exactly. Even if a neuron gets negative inputs, it still has a small non-zero gradient. It keeps learning. It doesn't die. This helps information flow better, especially in really deep networks, like, over 40 layers deep.
So a smoother curve avoids dying neurons. What was the impact in practice? Did it actually work better?
Oh, yeah. Google's own tests, replacing ReLU with Swish in their Inception ResNet v2 model, showed like a 0.6% to 0.9% accuracy boost on ImageNet. That's significant at that scale.
Wow.
And it's been shown to work well in various places. CNNs for images, RNNs for sequences, even GNs.
Okay, cool. Next up, Mish. That's got a bold nickname, the multi-purpose activator. What's its story?
Mish is mathematically a bit more complex, x times the tan of the soft plus of x.
Okay.
But the key thing about Mish is its smoothness. It's what mathematicians call C-infinity continuous. It's infinitely differentiable.
Infinitely differentiable. Why is that good?
Think about the network trying to find the best solution, the lowest point in this complex error landscape.
Yeah.
Sharp corners, sudden drops, they make it hard for the optimizer to navigate smoothly.
Right, could get stuck or overshoot.
Exactly. Mish provides an incredibly smooth landscape. It's like giving the optimizer a perfectly polished, frictionless slide. It just glides towards the best solution more easily, making training more stable and often more effective.
So, super smooth for better optimization. How does it perform?
It's consistently done really well, often beating both ReLU and Swish in comparisons. Like in one study on defect detection using YOLO 8, it hit over 90% accuracy, quite a bit better than the others. It also seems to be more robust if your data is noisy.
Sounds great. Is there a catch?
The main trade-off is computational cost. It takes longer to compute Mish for each neuron during training compared to ReLU or even Swish. So each training epoch takes more time.
Ah, the classic performance versus cost trade-off.
Yep. You might get better results, but it'll cost you more compute time.
Makes sense. And the third one you mentioned, GELU, Gaussian Error Linear Unit. Sounds probabilistic.
It absolutely is. GELU takes a different approach. Instead of just switching on or off, it uses what's called a probabilistic gating mechanism.
Okay, what does that mean in practice?
It essentially scales the input x by the probability that a random variable from a standard normal distribution is less than or equal to x. Think of it as weighting the input based on how likely or significant it seems, according to a Gaussian curve.
So it's not just a hard gate, but more like a dimmer switch based on probability.
That's a good analogy, yeah. It's smoother than ReLU, continuously differentiable, and it even has that non-monotonic property, a little wiggle around 0.
What are the advantages of this probabilistic weighting?
It allows for more flexible learning, captures nuances better, and one really standout feature is its noise resistance. It's supposedly much, much better, like 100 times better than ReLU at handling noisy inputs, especially those near 0.
100 times. That's huge. Where is GLU making the biggest impact?
GELU has really become the standard, the de facto choice in modern transformer architectures.
Like BERT and GPT.
Exactly. BERT, GPT, vision transformers. GELU is likely running inside those huge models, powering a lot of the recent breakthroughs in natural language processing and computer vision.
Wow. Is it computationally expensive like Mish?
The original formula involves the Gaussian CDF, which can be a bit slow, but there are really good, fast approximations that work almost just as well in practice. So it's become very practical to use. So yes, Swish, Mish, GELU, they represent this move away from simple switches towards more adaptive, nuanced functions that let networks learn much more complex things.
That evolution makes a lot of sense. Now, shifting gears slightly, you mentioned some functions have stability kind of built in, like they regulate themselves. SELU comes to mind.
Yes, SELU, Scaled Exponential Linear Unit. That one's quite unique. It uses these very specific mathematically derived constants, alpha and lambda.
And what do these magic constants do?
They enable something called self-normalization. As the data flows through the network layers, the activations automatically tend to converge towards having a zero mean and unit variance.
Okay, so the network kind of keeps itself stable automatically. What's the big win there?
It's huge for training deep networks. It inherently prevents both vanishing and exploding gradients, and the really big practical benefit, you often don't need batch normalization layers anymore.
Oh, wow. Batch norm can add complexity in computation.
Exactly. Removing them simplifies the architecture, potentially speeds things up. Plus, SELU also handles negative inputs in a way that prevents dying neurons, similar to Swish, but with this normalization property baked in.
So, sounds amazing. Are there any catches? Does it just work anywhere?
No, there are strict conditions. You have to use a specific weight initialization, Likuna normal. Your input data must be standardized, zero mean unit variance. And if you use dropout, you need a special variant called alpha dropout.
Ah, okay. So you need to set things up just right.
Yes. And it tends to work best in deep, fully connected networks, like MLPs, maybe less so in standard CNNs compared to other functions. And beyond these fixed functions, there's an even more exciting direction: trainable activation functions.
Wait, the function itself learns. It's not fixed anymore.
Exactly. Think of universal activation functions, UAFs, or things like parametric ReLU, DRAELU, where parameters within the function are learned during training.
How does that work?
Well, some approaches, like adaptive blending units, learn coefficients to mix multiple basic functions together. Others, like parametric RSIGLU, learn slopes for different parts of the function. The network essentially optimizes the activation shape for the specific task it's learning.
So the network figures out the best activation for itself.
Pretty much. There are examples like adaptive piecewise linear units, or PLU, that have shown really significant error reductions on benchmarks like CFAR10 just by letting the activation adapt.
Wow. So it's not just doing math, it's learning how to do the math better for the problem at hand. That feels like a major shift.
It really is. It views the activation function as another learnable part of the network, boosting expressivity and potentially cutting down on all that manual hyperparameter tuning we usually do. And if we look even further out to the real cutting edge, we see even more specialized functions emerging.
Like what? Give us a glimpse.
Well, there are Siren's sinusoidal representation networks.
Right, you mentioned those briefly, sine waves.
Yeah, the sine is the activation. They are amazing for tasks involving implicit neural representations, basically representing things like images, audio, or 3D shapes as continuous functions. They're key for things like NERF, creating those photorealistic 3D scenes because they capture high-frequency details really well.
Fascinating. Anything else?
There are physics-informed activation functions being developed specifically for PNs, physics-informed neural networks, where the function shape helps solve specific scientific equations like PDEs.
Tailored for science problems. Cool.
And then you get into even more exotic stuff like quantum activation functions for potential quantum AI systems.
Quantum activations. Okay, now we're really pushing boundaries.
It's early days, but yeah, exploring quantum properties and things like tunnel diode functions for neuromorphic hardware that mimics the brain, or even oscillating functions inspired by biological neurons. It's a huge space of innovation.
Okay, this is incredible, but it also sounds overwhelming. If you're actually building an AI model today, with all these options, ReLU, Swish, Mish, GELU, SLU, maybe even trainable ones, how on earth do you choose? There must be trade-offs.
Absolutely. That's the key practical question.
Yeah.
And honestly, there's no single best one. It always depends.
Okay, so what are the main things to weigh up?
First is that performance versus computational efficiency trade-off we talked about.
Right.
ReLU is still the fastest, computationally cheapest. Swish is pretty efficient. Mish often gives better accuracy but takes longer per epoch. GELU's approximations make it very practical despite its complexity. And SLU might simplify your whole network by ditching batch norm, potentially making it faster overall.
So how fast versus how accurate, basically? What else?
Robustness. How sensitive is it to other choices you make, like the learning rate or how you initialize weights?
Okay.
ReLU, for example, can be sensitive. A high learning rate can push neurons into the dead zone more easily. GELU, Swish, Mish, being smoother, tend to be a bit more robust, more forgiving.
And SELU?
SELU has that strict dependency we mentioned. You need the right initialization and standardized inputs for it to work properly. Yeah. It's less forgiving if you don't follow the rules.
Got it. And finally, just what kind of network are you building?
Exactly. Architectural suitability. GELU is the king for transformers, great for vision too, especially with the noise. Swish shines in deep CNNs, RNNs, GNs. Mish seems broadly applicable, good results in image tasks. SELU is really geared towards those deep, fully connected networks, the MLPs.
So you really need to match the function to the job.
You really do. No silver bullet.
Tying this all together, it feels like the future isn't just about scaling up models endlessly, but about making the individual components, like these activation functions, much smarter and more adaptable.
That's definitely the trend. We're seeing research focused on using AI itself, like reinforcement learning or evolution, to automatically discover new, better activation functions for specific tasks.
Whoa, AI designing AI components.
Yeah, and also hardware-software co-design. Thinking about the activation function and the chip it runs on together, designing them for efficiency, whether it's for low-power devices, future quantum computers, or neuromorphic hardware.
That makes sense.
It really underlines this shift. Activation functions aren't just static pieces anymore. They're becoming these learnable, adaptive elements that are crucial for pushing performance forward.
What an incredible journey we've covered. From those early limited functions like Sigmoid through the ReLU Revolution, its problems, to this amazing new wave of smoother, self-regulating, even learnable and specialized functions like Swish, GELU, SELU, Mish, and beyond.
Yeah, the evolution has been rapid and really impactful.
It's crystal clear the AI world has moved past needing one function for everything. We're heading towards, adaptive, learnable, specialized tools tailored for specific jobs and even specific hardware. So here's a thought to leave you with. Consider how these increasingly sophisticated, adaptable building blocks are quietly enabling the next wave of AI breakthroughs. It really makes you wonder, what other fundamental components of AI might be right on the edge of a similar kind of revolution? Food for thought. If you found this deep dive valuable and you want more insights like this into the cutting edge of AI, definitely hit that subscribe button. And hey, for more tutorials, visual explanations, and deeper dives into specific AI concepts, you can also check out Ian Ochieng AI, that's Ochieng on YouTube.
Good stuff over there.
Thanks so much for joining us on the deep dive. We'll catch you next time.